And now we can give some examples on integration. So, examples. First example is an Archimedean example, and it comes from problem linked to dynamics of ships and so on. But however, this is a very simplified problem with respect to the Archimedean, but area beneath the parabola. So again, this is a problem by Archimedes. And the problem is the following: just compute this area the area lying beneath the arc of parabola between 0, between the origin and the point of coordinate A. Okay, and so how to do it? And so the main idea is follow the construction of the integral. So define the partition. So consider the partition made of equidistance points so you have 0, which is equal to x naught, which is less than a divided by n, which is x1, less than 2a divided by n, which is x2, up to na divided by n, which is a, that coincides with xn. This means that we are just so let me cancel this coloring here. We are partitioning, too much. Partitioning in an equal way this interval. So here we have, for instance, a divided n, here 2a divided n, 3a divided n, and so on and so on. Okay. Now this is a partition, and of course we can compute the lower sum and the upper sum. So start with the lower sum, and the lower sum is very easy because consider the first interval. The first interval is here, from 0 to a to n, and here the infimum is 0. So here there is no area to be taken into account. For what concerns the second interval, here we have an area here to be computed. And how much is this area? This area is here, the height, always this mistake. The area here is the height of this point, and here is a squared divided by n squared, and the basis is very simply a over n, because it is 2a over n minus a over n. So go on and on. And here we have 4a squared over n squared. This is, and so on. And here we have 9 a square over n square, and so on and so on. So here we construct the lower sum, and from the computation that we have here, it is immediate to saying that s of the function f p is, of course, I forgot to tell you, but this is y equal to x squared between 0 and a. You understood, but I have to write it. So this is simply a squared divided n squared plus 4 a squared divided n squared up to what? When we go for the last, here we have the height, which is n minus 1 squared, a squared divided n squared. And this is the last rectangle. So up to n minus 1 squared divided by n squared, a squared. These are only the heights, and then every height has to be multiplied by the basis, by the value of the basis, which is always the same. So we can collect it out, and we have a over n. So from this sum we can collect a cube over n cube, and here we have 1 plus 4 plus 9 plus up to n minus 1 to the square. This is the sum of the first n minus 1 squares. Okay, so to say this is equal to a cube over n cube, sum for j going from 1 up to n minus 1 of j squared. Remember the formula that I gave you. So formula of the sum of the first n squares. We know that sum for k from 1 to, let me call it m. It is easier. From 1 to m is equal to m plus 1. Here 2m plus 1 divided by 6. Here we have to replace m by n minus 1. And so here we have n minus 1 times n. Here it will be 2n minus 2 plus 1. So we have 2n minus 1 divided by 6. We can write it in by performing here the multiplication. So we have by a cube n cube. So we have here a cube over 6, and then 2n cube, and here minus 3n square, if I am correct, plus n divided by n cube. Okay, and this is the lower sum with this so-called democratic partition in which all elements are equal. And let me consider the upper sum, and let us construct it, and we can do it quite fast now using the purple, for instance. Here we have again a square over n square, which is the height for the first triangle, and then the second is here for a n square over n squared, and the third with 9 and so on, and the fourth, and so on, and so on, and so on. Sorry for the superposition, but so I think everything is quite clear now. And for the upper sum, we have here to sum a squared over n squared plus 4 plus 9 up to n squared, a squared over n squared. So the upper sum is capital S Fp is equal this time to a squared over n squared plus 4a squared over n squared plus dots plus a squared times a over n. And this is the sum of the first. So let me act as before, it is clearer. So we have a cube over n cube, 1 plus 4 plus 9 plus, and then plus n squared. And here you have the sum of the first n squares. So therefore, we end up with a cube over n cube n plus 1, 2n plus 1, which means divided by 6, of course, which is a cube over 6 which is a cube over 6 and n cube plus 3n squared plus n divided by 2. No, sorry. Here there is n cube and here there is the 2. Okay, good. So here therefore we have that S Fp, which is equal to a cube over 6, 2n cube plus 3n squared plus n divided by n cube, of course is less or equal than the lower integral between 0 and a of the function x squared dx. And this implies then, by permanence of sign, if you want, also the limit here of a cube 6, the limit for n going to plus infinity of 2n cube plus 3n squared plus n over n cube is less or equal than the lower integral from 0 and a of x cube in dx. But this limit is very easy because this factor here goes to 2 because it is the ratio between the terms of numerator and denominator of the highest power. So here we have that a cube over 3 is less than 0 and a x squared in dx. So in a completely analogous way, we have that the upper sum S Fp is equal to, oh sorry, here there was a mistake. I did the upper sum. This is a minus, and this is a minus. The final result is not affected at all. So SFP is equal to a cubed over 6. This time one has to use the plus sign, 2n cubed plus 3n squared plus n divided by n cubed. And this, of course, is larger than the infimum of upper sums, which is the upper integral 0 and a x squared dx. So, again, the limit for n going to plus infinity of 2n squared, 2n cubed plus 3n squared plus n divided by n cubed is larger or equal than 0 and a of x squared dx. So again, this is a cube over 6 here. So again, this is a cube over 3. It's larger or equal than the upper integral. Therefore, putting all together, we have that we have that a cube over 3 is less than the lower integral, so the integral between 0 and a of s squared dx, which by definition is lower than the upper integral 0 and a x squared dx, which is less than a cube over 3. So notice that this is a cube. Notice that here the first and the last are equal. So at the end, the only possibility for this chain of inequality to hold is that all less or equal are equal. So therefore, so it is a sort of circular stuff. So it holds only if all signs here are equal. Therefore, all less or equal are equal. Then, in particular, we have that lower integral is equal to upper integral. Then the function is integrable. In the interval 0, a, and the integral between 0 and a of x squared dx is a3 divided by 3. Okay? And so we were able by this method to compute the area here, or if you want to define the area. Just applying the definition. Second example. So as an exercise, you can try to do it. So compute the area beneath the graph of the exponential between the points x equal to 0 and x equal to a larger than 0. This is another exercise, and another example, this is homework. Another example is the Dirichlet function. So Dirichlet function is, as you already know, the following. You have f from the interval 0, 1 to r that associates to every x the value 0 if x is rational and 1 if x is not rational. Now, now let P be a partition of the interval 0, 1 and see what happens. So, if you want to remember a bit the graph of 0, 1, of the Dirichlet function, here you have 0, 1, and then here you have 1, it is the level of irrationals, and 0, the level of rationals. So remember that both numbers, irrational and rationals, are dense. This means that whatever partition you take, whatever subinterval you take of 0, 1, so let E contained in 0, 1 an interval, then the supremum of f of x for x in I will be always 1, because there are irrationals in I, because irrationals are dense, and the infimum of f of x for x in I is 0. Therefore, let's go to lower sums, and so you have that lower sums S, Fp, which are sum for j from 1 to n, so the infimum f of x in x j minus 1 xj times xj minus xj minus 1. This is always equal to 0, because every infimum here is 0. On the other hand, and this implies that since it is true for every lower sum, as a consequence, the lower integral a b of f of x dx is equal to 0. You go to the upper sums, and then you have capital S Fp and sum j from 1 to n of the supremum of f of x for x belonging to this interval xj minus 1 xj times xj minus xj minus 1. And this is all, this stuff here is made of points all equal to 1. So what you get at the end is just the sum for j from 1 to n of xj minus xj minus 1, which means xn minus xn minus 1 plus xn minus 1 minus xn minus 2. This is a so-called telescopic sum, so minus x naught. Telescopic means that in couples everything goes away, like when you stretch a telescope and then you compress it, everything cancels, and you end up with xn, which is 1, x0, which is b, so this is equal to 1. And again, this is true for every lower sum. So the upper integral of the function of Dirichlet is equal to 1, which is different from 0, that is the lower integral. So since the upper integral is different from the upper integral, then f is not integrable, even though it is bounded. So we learn that there are non-integrable functions, and we also have the intuition that in order to be non-integrable, a function must be quite pathologic, like the Dirichlet function. Then I give you another function which is very interesting. I leave you I leave the question open. So, again, this is the Riemann's function to our hero for the integral, Bernard Riemann. So, Riemann's function, that is the following. You have f from 0, 1 to r that associates to every x the quantity 0 if x is rational. Sorry, is irrational. And the quantity 1 over q if x is rational and of the form p over q, where p and q, of course, have no common divisors. And this is quite a funny function because, so let us look. So it is, okay, 0 at 0, we can also add 0 here, and 1 at 1. Then it is 1/2 at 1/2, 1/3 at 1/3, 1/3 at 2/3, 1/4 to 1/4, and 1/4 to 3/4, and so on and so on. So my question is Riemann's function integrable? And if so, what is the value of its integral? Okay, this is the question, and then we stop the example, and then we move with the theory in the next video.